Do you see my screen?
Yes, sir.
Okay, so in the last class, I gave you an introduction to organometallic chemistry, and we looked at a few things as a brief introduction, how this chemistry came into being, and what are the important aspects. So, the most important thing that is there in organometallic chemistry is the metal carbon bond. Okay, and based on this only, you have several different variety of compounds, organometallic compounds, that we will be studying, especially two types that I briefly introduced in the last class. One is called as the sigma complexes, and the other are the pi complexes. And I'm going to give you some examples with respect to each of these. So I gave you the example of a sigma complex by talking about a sigma bond uh, in a organic molecule, where a sigma bond is formed by the head-on overlap of two orbitals that are forming the bond. So when you talk about a metal carbon sigma bond, okay, it's more like the uh, carbon and metal are sharing their electrons by the overlap of the orbitals. I think I showed this picture last time. So from the metal you have an orbital like this, and from the carbon you have an orbital like this, and they overlap, and so you form a region around metal and carbon where there is electron density that is shared. So this will be the dense region where one electron from metal and one electron from carbon will be shared. In that sense, it is very similar to a carbon hydrogen covalent bond. Very similar. The only difference being that it is the metal orbital which is forming the bond and not the hydrogen orbital. That's the only difference. Okay. So soon I'm going to introduce something called as the effective atomic number concept, or the 18 electron rule, that I'm going to show you shortly. And in order to get there, um, it is actually a method to count the number of electrons in the valence electrons in a organometallic complex, and usually it follows the rule called as the 18 electron rule, and it's kind of similar to the octet rule that you had studied for atomic stability. So it's somewhat similar to that. I'm going to introduce that a little later. So before going there, I want to give you some of the examples of ligands which can form sigma complexes and pi complexes. Now, what is a pi complex? Okay, pi complex is um, an organic ligand. I will take the example first and then explain. You have ethylene as an example, and we already saw this example, the Zeiss salt that we saw in the last class. So this double bond is formed by the, you see, the head-on overlap of the sp3 hybridized orbitals will form the sigma bond, and then you have the pure p orbitals on the carbons. So those which are having the same symmetry now will overlap in a sideways or a lateral fashion. This is what you have studied in your lower classes. Okay, so these orbitals, in fact, when they overlap, sideways overlap happens, they form something like this. So you have the carbon and carbon. So here is the sigma bond, and you have something like this called as the pi bond, so, and on the top as well as on the bottom you can see. This is where the electron density of the pi bond will reside. Now this can be donated to a metal. So usually pi bonds to a metal are shown like this. From the middle of the bond, there is donation to the metal. So the pi electrons are donated to the metal. Now the bonding characteristics between the metal and the pi bonds are very complicated. I mean, it's actually not that complicated, but it is little too much for me to explain to you guys, because I have to explain several other concepts of molecular orbital theory. So I'm not going to do that. It will be too much for you to grasp. Okay. But what is important for you to note is that the pi electron density is the one which is donated to the metal, and bond is formed. So even though I'm showing the bond to the metal starting from the middle of the double bond, it actually indicates that the electron density belongs to both the carbons. So this carbon as well as that carbon is involved in bonding to the metal. Okay. Soon I'm going to introduce you to something called hapticity, which is indicated by the Greek letter eta. Okay. I will explain what hapticity, and hapticity plays an important role in understanding pi bond, or if you understand hapticity, pi bonding can be easily understood. Okay. So there are a number of pi electron donors, ligands that are available. I'm going to show you some of the classic ligands that you generally come across, quite a few of them, and then we'll move forward. Okay. Now, when it comes to pi complexes form a covalent bond with the metal, and as I told you, usually in a metal carbon bond, the metal is usually electropositive. So you kind of give it a partial positive charge, and the carbon is negative, partial negative charge. Okay, in that sense, a pi complex can be formed with a number of ligands. I will give you some simple ligands. So not a pi, sorry, a sigma complex. So I will give some of the simplest ones, sigma ligands. Let's say sigma ligands. One of the simplest one is the methyl residue. This can form a metal methyl bond. And you see this carbon to metal bond again here is very similar to the carbon to hydrogen covalent bond. Okay. So in that sense, this methyl ligand can be considered the equivalent of a methyl anion. So in organometallic chemistry, sigma bond forming ligands are in general considered to be negative charged anionic ligands. Now in your coordination chemistry, you have studied about anionic ligands. For example, you have chloride, bromide. These are very classical anionic ligands, OH minus, you see, and so they donate their electrons to the metal and they form a bond. So something similar to that can be viewed here, even though the bond between the carbon and metal is slightly more covalent than what you would expect in a coordination compound. Okay, so CH3 minus. So now what is this in general called? This is a methyl. This is a methyl anion, and in general you can call it as an alkyl anion. Or in other words, any metal alkyl bond will be a uh, sigma complex. Okay, so for example, I can simply write Rm. Now this sounds very familiar, because if I add one more Mg and Br or Cl, it talks about a Grignard reagent. Okay, so you see, it's nothing but a alkyl magnesium bond as a particular example. But instead of that, if I simply if I simply say it's a metal, then you are talking more in general. Okay, now this is very important for you to know, because soon we are going to consider this anionic uh, organic ligands uh, in terms of their electron numbers, and we are going to do some calculations based on that. So you need to keep this in mind. Okay, so these are sigma ligands. What are the other sigma ligands? So any alkyl group, for example, I gave you methyl, it can be ethyl, so it can be uh, CH3, CH2 metal. Similarly, propyl, alkyl, I mean propyl, butyl, pentyl. These are considered to be sigma ligands. Then we go one step further. You can have aromatic compounds also coming in this category. So you have phenyl. You know that there is a carbon hydrogen bond here. Now instead of a hydrogen, now it can be replaced with a metal. So again, a classic example for that is phenyl magnesium bromide, another type of Grignard reagent. Okay, then let's go and check out some pi ligands. Okay, so when it comes to pi ligands, you can have alkenes and alkynes. Both can be pi ligands. Okay, um, what I will do is move it down. I'm moving it to the next page, because some more sigma bonded complexes, I need to give you some examples. Uh, okay, so when you take an alkene, I told you here that the pi electrons can be donated to the metal. Okay, but even in an alkene, the metal can also replace one of the hydrogens as if it is a sigma. It is a sigma donor. So in that case, alkenes can also be a sigma. They can form sigma complexes. So it can be like this: double bond. Okay, now there is a big difference between the metal forming a sigma bond with carbon and the metal forming a bond through the pi bonds of the carbons. There's quite a bit of a difference. Okay, so this is purely covalent in nature. In this one, it's a more a donation of the pi electrons to the metal. Okay, so because of the pi electrons, uh, the bonding is related to both the carbons. But in this case, the bonding is related to only one of the carbons. So keep this in mind. Okay, so this is also a sigma bond. So if a alkene can form a sigma bond, an alkyne can also form a sigma bond. So you have acetylene, some R group, it can be hydrogen also, and this carbon can directly bond with a metal. So this is also a sigma bonding complex. Okay, so these are some of the examples of pi ligands, sigma ligands. And remember that the ligand residue is always considered in a organometallic compound for a sigma complex. The ligand residue is always considered to be an anionic ligand. Okay, so in this case, the ligand here will be R C triple bond C minus. Okay, similarly here it will be CH2 double bond CH minus. They are all considered to be negatively charged. So in this case, for phenyl, it will be phenyl anion and so forth. Okay, so they are always considered to be negatively charged species. Okay, this comes very handy in certain calculations. Okay, so alkenes and alkynes. So I already told you carbon-carbon double bond binding with a metal. Now carbon-carbon triple bond can also bind with a metal. Now you may ask, there are four electrons in an alkyne, four pi electrons. So here there are only two pi electrons. Here are four pi electrons. So can we consider it as a four electron donor? No. Okay. Even though alkynes can also form a pi bond, pi donation, it is only considered as a two electron donor. This is also a two electron donor. Okay, so please keep that in mind. There are explanations why you cannot consider more than two, but I'm not going to go through that. Even if you read it from the textbooks, you will get confused. So I'm not asking you to do that. Okay, so these are okay. So uh, the pi electron donor that I have shown in terms of alkenes and alkynes. There are a few more examples. Another classical one is benzene. Benzene has 6 pi electrons, and all 6 pi electrons can be donated to a metal, and so sometimes it can be donated to a metal. Only two of the pi electrons are donated. These are very rare cases, but in benzene you can find these kind of complexes, all the 6 pi electrons being donated to a metal. So in this case it's a 6 electron donor. Now this will be, when you study about this is a new concept. Probably for the first time you are hearing something like this, a 6 electron donor through a single ligand. Okay, so I will come to the concept of hapticity and explain it much more clearly. Okay, so a few more examples I want to show you. There is also another pi donor uh, called as cyclooctadiene. Okay, cyclooctadiene. What is the cyclooctadiene? So first of all, you have to draw a cyclooctane. Okay, so this is cyclooctane and it's a diene. So one double bond here and one double bond here. This is a cyclooctadiene molecule. This molecule, both the uh, double bonds can donate to a metal, something like this. Okay, so like this, but it looks like the metal atom is going into the center of this cavity, but it is not like that, because the metal atom is far bigger than the cavity here. So I mean, how do I know that? I mean, it's just an illusion created by writing a small sized metal atom, but in reality the metal atom is as big as the molecule itself. So in reality you have a shape like this. The molecule cyclooctadiene folds itself like this, two double bonds, and then they will donate it to the metal. Okay, I have drawn it terribly. Not, I cannot say that I draw it very well. I'll show you an example. I'll just give me a moment. Take a look. Take a look. So this, whatever molecule you see here, is nothing but COD, cyclooctadiene. It's just folded in certain fashion. It's available like this. Okay, so these are some of the pi, uh, some of the ligands which can form pi bonding with metals. Now I'm going to come to one more category, a special category called as carbonyls, which I talked about in the last class. Carbonyls. Okay, this is a very, very simple molecule, just carbon monoxide. Okay, carbon monoxide can also bind to the metal. So you have classic examples for this. For example, nickel tetracarbonyl. This is a very, very famous complex. Okay, and usually the binding to the metal is through the carbon. And these compounds are more pi bonding than sigma bonding. So even though you may find structures of these compounds, like this CO, like this, you will find it in the textbooks. It's shown like this, and the carbon nickel bond suggests that probably it's a covalent bond between carbon and nickel. And as I told you in organometallic chemistry, the carbon metal bond is considered to be formed between an anion and the metal. That's what I told you. Even though it may feel like that because you simply draw like this, it actually is a pi bonding ligand, and particularly something called as pi accepting. Okay, this is a new concept. I'm not going to go into the details, but briefly I'll tell you the difference between the pi bonding that you see in the earlier cases, like for example, cyclooctadiene, pi bonding with metal, and pi accepting in carbonyls. The difference is that here the pi electrons are donated to the metals, but in pi accepting complexes, the metal electrons are pushed into the carbonyl. Now that is something unusual. You never heard of this kind of bonding, but this is called as back bonding. Okay, it is called as back bonding, and this back bonding happens. Again, I'm going to very briefly discuss this. It happens because carbon monoxide has what are called as anti-bonding orbitals located on the carbon, and the metals have d orbitals, and these will overlap like this. The d orbital. These are the metal d orbitals, and these are the pi star, the anti-bonding orbitals of carbon monoxide, and they have very similar shape and they have very similar energies. As a result of which, some of the metal electron density which is built up by the donation of electrons from other ligands is pushed away from the metal into the carbonyl. So in that case, carbonyl is a pi accepting. Why is it pi accepting? Because it has pi orbitals which accepts some of the electron density from the metal. Okay, so in this case, a classical ligand to metal donation only is not considered. There is some donation from the metal to the ligand also. Now this may be a new concept for you, and I don't want to elaborate too much on this. It will be confusing for you. Just enough for you to understand that it is called as pi accepting ligand, carbon monoxide. Now because of this pi accepting nature, carbon monoxide is a strong field ligand. It's a strong field ligand. Again, I'm not going to explain why. Okay, so how many categories have you seen? Sigma complexes with alkyl residues, and pi donating ligands like alkenes, alkynes, and a few others, and pi accepting ligands like carbon monoxide. Now there is one more category where the first two are combined together. That is sigma donation as well as pi donation, both will take place in certain ligands. I'm going to start with the most prominent of them, called as the allyl anion. Okay, what is this allyl anion? So you have a carbon double bond carbon and a single bond carbon where there is a negative charge here, the ligand. Okay, so if you can fill it up with hydrogens. This is a allyl anion. Simply, if you want to write it in terms of stick figures, you can put it like this: a double bond and a negative charge on the end terminal carbon. Now, if you know about resonance structures, this can be in resonance with this structure. Okay, how this negative charge can move in, and this bond can, you can push it this way. If you know what electron pushing means in chemistry. Okay, so this can be pushed inside to this carbon, and this double bond will break in such a way that the pi electron density is given to this carbon. So what happens? This develops a negative charge. Since the electrons are pushed, this loses its negative charge and becomes neutral. So it's like this. Okay, so in effect, it forms a resonance structure like this. Like a partial double bond is between the three carbons, and then together contributes, it has a negative charge. Okay, so now this whole thing can donate electron. So like this, usually in textbooks it's written like this, to a metal. So what kind of a donation is it? It is the two pi electrons and the negative charge combined together, which are donated to a metal. So this is a very special type of a ligand. Okay, so allyl ligand. Now, unfortunately, so I'm sorry to complicate it a little bit. This allyl group can also be a simple, very simple sigma donor as well. How? You see, this allyl anion, only when it combines with the double bond, it becomes a allyl anion like this donor. Okay, if it doesn't combine with the double bond, simply this anion in the terminal carbon just forms a bond with the metal, then it will become a simple sigma donor. So in which case I will combine it here, and I will simply write it like this. You see here, this is formed by the allyl anion contributing, sorry, donating it to the metal, forming the carbon metal bond, in which case it's a sigma complex. Okay, another very famous ligand in the same in this category is what is called as the cyclopentadienyl anion. Little bit slightly more complicated, but the concept remains the same. Here you have a cyclopentane ring with two double bonds. Okay, now if you simply draw the structure, it looks like it will be a pi donor. Okay, but when you generate a anion here in this carbon, what happens? Due to resonance, this anion can move places. Okay, so it can form, it can be here, and this again the next resonance structure. I know that this will take a little bit of time for you guys to study. Nevertheless, you have to study. Okay, and it can be here as well. So again, you can keep moving it, and so a number of resonance structures are formed, and as a result, just like how you had one single structure having a hybrid bonding, similarly, this whole thing can be considered as like this, like benzene, the negative charge. Here also it should be a negative charge. Okay, so this is called as the cyclopentadienyl anion. Now I'm going to uh, talk about one simple way to understand these kind of complexes, and that's where you have what is called as electron counting. Okay, so there are two different methods of electron counting which I want to teach you, and I'm going to do that now. Why do we need this electron counting? For the simplest reason. Okay, so let's come to electron counting in OM chemistry. What is this electron counting and why do we have to do this? Okay, let me give you a little background. Okay, a scientist by name Sidgwick, I think, yeah, N.V. Sidgwick, 1920s, he recognized that many organometallic compounds have the same valence electron count as the noble gas that terminates the long period to which the metal belongs. I'll give you one example. Let's take this example, nickel tetracarbonate. Okay. He found out that the valence number of valence electrons in nickel tetracarbonyl is 18. Okay. And 18 is the electron count in the period where nickel appears, and that belongs to krypton. Okay, krypton. That yeah, krypton 36. If you take krypton 36, which is a noble gas, okay, you can write its electronic configuration, and the valence configuration will be 3s2 uh, is it 3s2 or 4s2? I think it's 4s2, 3d10, 4p6. Okay, this is the valence configuration. You add it up, it gives you 18 electrons. Okay, so just like your octet rule in molecules where octet rule is followed, the molecule will be stable. Sidgwick found out that transition metal organometallic compounds, when you count the electrons in the valence shell belonging to the metal as well as the ligand which has contributed its electrons, when it counts to 18, he found that the complexes were exceptionally stable. They were very stable. So this was called as the 18 electron rule later. What does the rule state? It's very simple. An organometallic complex of a D metal, D block metal, when it forms, it tends to have 18 electrons in its valence shell. This is a general rule. There are exceptions. In fact, for one class of compounds, the rule is that if it has 16 electrons, it becomes stable. Okay, that's an exception. I'll give you some examples. Now, how do I say that nickel tetracarbonyl has 18 electrons? Okay. Now, before we go there, carbon monoxide is considered to be a neutral ligand or a charged ligand. That's something important for you to know, for you to consider first. Carbon monoxide is considered to be a neutral ligand, and its donation to ligand nickel, it considered to donate 2 electrons per carbon monoxide, just like your coordination chemistry that you had studied in the past. Only thing is you never counted the electrons, but in the case of organometallics, you count the electrons. So carbon monoxide is a neutral ligand capable of donating 2 electrons, just like your ammonia or water molecule. I hope you guys remember. Okay. So if that is the case, let's count the electrons. Now nickel valence electrons. Now nickel is in zero oxidation state. Why? Because the ligand is a neutral ligand, so no charge, and the whole complex also doesn't have any charge. It's a neutral compound, which means that nickel charge is also zero. So nickel is in zero oxidation state. So what is it? What is its valence electronic configuration? Again, I'm showing only the valence configuration. It will be 4s to 3d8. Okay, 4s to 3d8. Count. Combine them. The metal valence electrons will be 10 in numbers, right? Now each carbon monoxide contributes 2 electrons. So 4 into carbon monoxide will be equal to 8, and you add them, you get 18 electrons. Do you see that? So this is how nickel tetracarbonyl contains 18 electrons. We arrive at it. Now this is a very simple compound to calculate for two reasons. One is your ligand is a neutral ligand. It's very easy to consider them as two electron donors, and the metal is in zero oxidation state. So you totally consider its valence electrons, but not all compounds are like this. Okay, some of the complexes carry a charge, and some of the ligands are not neutral, but they are charged or mostly anionic complexes. So what do you do in terms of these? So there are two ways that you can do the counting. Okay, so one method is called as the neutral ligand method. Neutral ligand method, and the other one is what is it called? I forgot the donor pair method. I'm going to explain both these. I'll start today. Okay, donor pair method. Okay, now one of the differences between these two methods is here in the donor pair method, the metal oxidation state is determined. Okay, the metal oxidation state is determined whether it is in +2 oxidation state, +1 oxidation state. But in neutral ligand method, the metal oxidation state is not determined. Okay, so you simply consider the valence electrons. Only the valence electrons are counted. Okay, so you never bother to find the oxidation state of the metal in neutral ligand method. Both of them will give you the same count, but they are slightly different methods. Now, in order to determine the metal oxidation state, a clear differentiation between neutral and anionic ligands has to be made. Clear differentiation. Okay. Here also you differentiate between neutral and anionic ligands, but you don't seek to find the oxidation state of the metal. Okay, how do you apply these things? I will give you one example, a mixed example, and then we will learn how to apply this. Let's take this example, this complex. This is iridium. Iridium is in which group? It's in cobalt group. Okay. So if you look at the periodic table, you have cobalt, rhenium, iridium. This is how it is. Okay, which means that uh, whatever valence electrons you have in cobalt, it will be the same thing, only in different shells. Okay, so let me draw the structure. Iridium, dibromo, methyl, CO thrice. This is the complex. Okay, this is the complex. So how do you find the count? Okay, now if you look at iridium, let's do the neutral ligand method. The oxidation state of the metal is not determined. So you just take the valence electrons. Okay, and then I will tell you what kind of electron donors each one of these ligands are. Okay, so I'll explain that and I will show you. Now iridium the valence electrons. Iridium is in the sixth row, so it will be 6s2 5d7. Okay, so totally 9 electrons. Okay, now bromine considered to be bromide ion, 2 are there. So okay, then methyl considered to be methyl anion, 1. Okay, then carbon monoxide, already told you it's a neutral ligand. So how many are there? 3 are there. So 3 into 2, 6. Now why did I not write what is the number here? Here I have written, but that's wrong. Why did I not write how many electrons? The reason is in the neutral ligand method, okay, since you are not seeking to find the metal oxidation state, each anionic ligand is considered to donate 1 electron. So please remember this. This is important. It's considered to donate 1 electron. It's a 1 electron donor. So in that case, 2 into 1 will give you 2. 1 into 1 will give you 1. Now you add it up. How much do you get? 18 electrons. Okay. So you need to know which complexes, which ligands will form sigma. See, remember, bromine as well as methyl, they also are sigma bonding with the iridium. Okay, because they are negatively charged ligands. Okay, now let's do the other method in which almost all these things are considered almost exactly the same, except that you seek to find the oxidation state of the metal, and each of the anionic ligand is a 2 electron donor in the second method. Which method is that? It's the donor pair method. Okay, so let's do that. So for that, in order to do the donor pair method, I have to find the oxidation state of iridium. So how do I find? You see that the total complex charge is neutral, 0. Okay, but it has 3 anionic donors. So uh, 2 bromide and 1 methyl. So 3 anionic charges, uh, anionic ligands. So X minus, sorry, sorry, X plus minus 3 equal to 0. What is the 0? 0 is the total charge of the complex. Minus 3 is the charge of the ligands. 2 bromines and 1 methyl. So that's minus 3. So X will be equal to plus 3. So the oxidation state of iridium is plus 3. Okay. So in that case, how many electrons will iridium contribute according to? So iridium 3 plus in this case will be 9 is what you have in a neutral iridium atom, but iridium 3 plus will have 3 electrons lesser. So that will be 6. Okay. Now comes the difference. As I told you, each anionic ligand is considered to donate 2 electrons instead of 1 electron in the previous method. So in that case, bromide will be 2 into 2, which will be 4, 2 bromide, and 1 methyl will be 2, and carbon monoxide, 3 carbon monoxides. I'll give you 6. Now you add it up, 6 plus 4, 10, 10 plus 2, 12, 12 plus 6, 18. See, you get the exact same result. So, what do I see in this method? We see that metals, D block metals, when they form organometallic complexes, they tend to have 18 valence electrons that can be counted by either the neutral ligand method or the donor pair method. What's the difference between these two methods? Let me summarize one more time. In the neutral ligand method, you do not seek to find the oxidation state of the metal. Instead, you use just the total valence electron count in the atom. Second thing is neutral ligands are considered to be 2 electron donors. and anionic ligands are considered to be 1 electron donors. And when you do the calculations, you get the total electron count. Now in the donor pair method, you seek to find the metal oxidation state. So that you can find by knowing which of the ligands are anionic in nature. So you should have certain amount of idea which is a neutral ligand and which is a non-neutral ligand. Okay. So, and in the donor pair method, both anionic ligands as well as neutral ligands, they are all considered to be 2 electron donors. Okay. So if that you do that, you will get the same electron counts in the both the things. Okay. Now quickly I want to tell you, neutral ligands. Okay. Neutral ligands are considered represented as L, and anionic ligands represented as X. Okay. So in that sense, carbon monoxide is a L type ligand, neutral ligand. Okay. Your ethylene is also an L type ligand. Okay. Now your cyclopentadienyl, this anion, you see there are two pi electrons, pi bonds and one anion. So it is a mixture of L and X. So it is considered to be L2X type of a ligand. Okay, L2X type. And benzene with three pi bonds and no anionic residue, it is a L3 type ligand. Okay, so now let's see L3 type. This is a 2 electron donor. This is also 2 electron donor. L2X is a 5 electron donor in the what method is that? The first method, neutral ligand method, and it is a 6 electron donor in the uh, donor pair method. Do you understand? This may, this may be slightly confusing, but if you apply your understanding a little bit, few times you read and study, you will easily understand. In the neutral ligand method, it is considered to be a 5 electron donor. How? 2 electrons for each of the pi bonds and one negative charge, so 1 electron. So 2 plus 2 plus 1 will be 5. But in the donor pair method, again 2 plus 2 plus 2, negative charge is considered to be a 2 electron donor. So it becomes 6 electron donor. Okay. Now the other type that I want to, so here it is in both the cases it's 6 electrons. No doubt about that. It's because it's L3. Where only when you get this X, you get slightly different numbers. Another example is the allyl anion. Okay, allyl anion is a LX type ligand. LX type. How is it LX? See, this is the ligand. So you have a double bond as well as a negative charge. So this is the L type and this is the X type. So it is a LX type. So in which case it will be a 3 electron in the neutral ligand method and 4 electron donor in the donor pair method. Okay. In the next class, I want to talk about hapticity, and I'll tell you how that one works. And watch out for a recorded video for tomorrow, and I'm going to give you recorded video based on which you will be doing some activity in the next class, which will be on Wednesday. So watch out for that. It will be made available tomorrow. I'll stop here, running out of time.
Sir,
Sorry.
sir,
Yes.
excuse me, sir. Sir, I have messaged you something.